Hello there, engineering physics. I am Dr. Wisby, and this is physics. Today we will be discussing the application of Newton's laws to equilibrium. And it's come to my attention that some of you may be watching these videos on fast forward. So I will be speaking extra slow during this presentation so that I sound, no, not gonna do that. I don't care if you watch on fast forward. You may want to turn on closed captioning so that you can absorb the knowledge even faster. It's up to you, I don't care. All right, let's get right to it. Chapter 5, it's going to be amazing. Very well. So, well, we're gonna go with the YouTube subtitles, but let's, oh, we're already having trouble. Oh, jeez. There we are, lecture presentation, chapter 5, applying Newton's laws. Yes. Okay, so these are good videos that you can watch later. We're gonna go through the presentation. Okay, so let's get right to it. Chapter goal: to use Newton's laws to solve equilibrium and dynamic problems. So in equilibrium, things are not moving. In dynamics problems, things are moving. Now you can have something called a dynamic equilibrium, which means that an object is moving, but it's in equilibrium. So for example, all right, so looking ahead to chapter 5, equilibrium problems. Let's look at this picture of the boy trying to push the sofa. The boy is pushing as hard as he can, but the sofa isn't going anywhere. It's in equilibrium. The sum of the forces on it is 0. Okay, so if you think about this problem, he's applying a force, but the force is not as great as the maximum of the force for static equilibrium. And remember, whatever the boy however much force the boy applies to the sofa is going to push back on him with an equal and opposite amount of force. So if the sofa is not moving, then it's going to push back on the boy, and so they're going to be in equilibrium. Okay, so we'll learn to solve equilibrium problems by using the fact that there's no net force. If there is a net force, the couch is going to start accelerating and it will start moving. But that is not the case because he's in equilibrium. Okay, Newton's laws allow us to relate the forces acting on an object to its motion, and so to solve a wide range of dynamics problems. So a dynamics problem is where something is moving, like a skier. So if a skier can maintain a constant velocity going down the hill, that means that there is no net force. And at some point you will hit a maximum value, and that is the point where the acceleration due to gravity is balanced by the force of static friction. At that point, that would be the terminal velocity for the skier. She would not be able to go any faster. It happens when you fall out of an airplane. You reach something called a terminal velocity. When you hit terminal velocity, you cannot go any faster. So when the skier is racing down the hill, that is the maximum velocity. Now, it may be a lot faster than you are comfortable with. Same thing with falling out of an airplane. There's also a terminal velocity when you're falling in water. The force of drag is much, much higher in water. So that means that you will sink at a certain speed as long as if you're not too buoyant. So I took scuba diving classes, and in order to get yourself to sink underwater with the scuba tank, you have to wear weights. And there's a certain rate that you can fall depending on how much weight you have on and how you adjust your scuba tank. And you can make yourself fall at a certain rate through the water, but that is going to be determined by the force of drag. So you've got these two competing forces, and if you were to reach your terminal velocity underwater, that would mean that you cannot fall any faster and you're in dynamic equilibrium. Okay, so we learned to draw free body diagrams showing the magnitudes and the directions of the force on an object. That is going to be extremely important in this chapter. And so we're going to do a lot with free body diagrams. We need to think about, okay, which way is friction? Which way is the motion? And so we have not seen the end of vectors. And we're going to use trigonometry to determine force in the direction of motion. So free body diagrams, very important. Okay, so an elevator suspended from a cable. It is moving upward at a steady speed, which is the free body diagram in this situation. Okay, so an elevator is suspended from a cable. It's moving upward at a steady speed, which is the correct free body diagram for this situation. I like to read the problems twice because I need to let it sink in. It helps me to understand what the problem is really asking for. Because a lot of times in physics, that's the main problem, is you don't understand what the problem is really asking for. So read it carefully. Okay, so the big clue here is that it is moving upward at a steady speed. That means its velocity is constant. The velocity is not changing, so that means there's no acceleration. So the forces are balanced. So let's take a look at our picture here. In the first picture, I see that tension is much bigger than the weight. So the forces are not balanced in this expression because this one seems to have a much bigger tension. Here, tension is the same as weight. It doesn't matter if the elevator is moving, you can still be in a dynamic equilibrium. If these forces were not balanced, then it would start to move. Okay, this one here, tension is clearly much shorter than the weight. That would mean that it's accelerating downward. And here, it looks like these two going up do not equal the one going down. They might be too short. And then E, F net is 0. When F net equals 0 vector hat, that doesn't mean anything. 0 is not a vector. You can't have 0 meters pointing in any direction. So that one's going to be a no on F net equals the 0 vector. What is the 0 vector? Okay. Reading questions. Which of these objects is in equilibrium? A car driving down the road at a constant speed. That could be. It's at a constant speed. It's not floating. If it were floating, that would not be. If it's going up, then that's not equilibrium. We don't have anti-gravity. Dr. Neutron, how is your anti-gravity device coming along? Please tell us what's going on with the anti-gravity device. So, which of these objects is in equilibrium? A car driving down the road at a constant speed, It's not accelerating. It's not slowing down or speeding up. It's not floating off of the Earth. So no anti-gravity device. Dr. Neutron, how's that anti-gravity device coming along? Why do you insist on asking me these pedestrian questions? You know as well as I do that the electromagnetic force is not related to the gravitational force. Therefore, there will be no anti-gravity. Obviously. Well, thanks for that, Dr. Neutron. As I was saying, which of these objects is in equilibrium? A skydiver falling at a constant speed. I fear I may have already given you the answer. A block sitting at rest on a table. So I think the answer is going to be D, all of the above. Indeed, it is. All three are in equilibrium. Remember, equilibrium does not mean the object is stationary. It means that the sum of the forces equals 0. So the net force is equal 0. Otherwise, it would be accelerating. The velocity would be changing. You're riding in an elevator that is accelerating upwards. Suppose you stand on a scale. The reading on the scale is going to be greater than your true weight, equal to your true weight, or less than your true weight. So perhaps you have ridden on a roller coaster and you can imagine the opposite. So as you start to fall in a roller coaster going over a cliff, you'll notice that you feel lighter. That's because you are starting to experience free fall. And so if the elevator is going up, you're going to feel heavier. And this is why you feel weightless in space, is because you're falling all the time. You are in a perpetual state of free fall. It's like you're falling down, but you also have a forward velocity. So as you go forward, you fall, and it's like you're always just missing the Earth. That's why many astronauts report that they are motion sick the entire time that they're in space. And the plane that they go on to train astronauts is called the Vomit Comet, because it goes up really high and then it will drop almost straight down. And so you get a couple minutes of weightlessness, and many people report that this is a very uncomfortable feeling. So if you are a person that is gets motion sick, then being an astronaut may not be for you. So what is the answer to this question? The reading on the scale is going to be greater than your true weight. Yes. All right. In general, the coefficient of static friction is smaller than the coefficient of kinetic friction, equal to the coefficient of kinetic friction, or greater than the coefficient of kinetic friction. In most cases, they are not the same. The coefficient of static friction is much higher. The coefficient of static friction is much higher, so it takes more force to get an object sliding than it does to keep it going. Once you get it moving, it's much less force than it was initially to get it going. Okay, so the drag force pushes opposite to your motion as you ride a bicycle. If you double your speed, what happens to the magnitude of the drag force? We looked at this last chapter. Maybe we went through drag a little too soon, but we know that drag is related to the square of the velocity, which means the faster you go, the more drag force you're going to experience. So the drag force is going to increase. Okay, so let's take a look at this. 2 boxes are suspended from a rope over a pulley. Each box has a weight of 50 newtons. What is the tension in the rope? All right, so if the boxes are the same, so 2 boxes are suspended in a rope, each box has a weight of 50 newtons. They are. So this means that it's in equilibrium. So the tension coming down this way is equal to the tension on this side. So it must be 50 newtons. Okay. If you start adding more pulleys in the correct way, you can gain a mechanical advantage, but it requires more pulleys. So the answer is 50 newtons. That was 50 newtons. Okay. Section 5.1, equilibrium. Watch this video, statics and dynamic equilibrium. We're not going to watch it right now, but you can watch it later. All right. So we say that an object is at rest in, well, let's watch the video. So please go watch this video, pre-lecture video, static and dynamic equilibrium. Wow, that was amazing. Oh man, I feel like I need more hair and a better shirt, but that's another issue. Okay, so we say that an object is in static equilibrium. At rest, an object at rest is in static equilibrium. An object moving in a straight line at a constant speed is in dynamic equilibrium. Dynamic means moving. In both types of equilibrium, there is no net force acting on the object. The object is not accelerating. If there's no net force acting on an object in the XY plane, there's no net force either in the X or the Y components of the net force. If it's in equilibrium, then the forces are balanced. There's no net force. So if I sum up my X and my Y forces, then they are perfectly okay. So that means all of my forces going this way are equal to all of my forces going that way. So if I add them all up, let's say F1 plus F2 plus F3 and so on, they will equal 0. If they do not equal 0, then you are not in equilibrium. There is acceleration. All right. So how do we solve these problems? The first thing is always read the problem carefully, because that is usually where people mess up. So if an object is in equilibrium, the net force acting on it must be 0. We'll use this fact to find the forces that keep it in equilibrium. And the clues to whether it's in equilibrium will say something like it's traveling at a constant velocity or a steady speed, or it's standing still. Those are a clue that you are in equilibrium. So read the problem carefully to determine if it is in equilibrium. And always remember, forces going left equal forces going right. Forces going up equal forces going down if it's in equilibrium. Okay, first check that the object is in equilibrium. Does A equal A0? No. An object at rest is in static equilibrium. An object moving at a constant velocity is in a dynamic equilibrium. And I have philosophical questions with them using the vector notation over 0. Okay, so maybe that's just me. First, check that the object is in equilibrium. Does A equal 0? An object at rest is in static equilibrium. An object moving at a constant velocity is in dynamic equilibrium. Then identify all forces acting on the object and show them on a free body diagram. Determine which forces you know and which forces you need to solve for. So it will give you in the problem, you will know some of the forces and you will have to solve for the other forces. So to do this, what do? We could say we use a system of linear equations, and the best way to do this would be to find the equation for your x forces and then find the expression for your y forces. Then you can solve for the unknown forces. Okay. So problem solving approach 5.1, equilibrium problems. An object in equilibrium must satisfy Newton's second law for the case where A equals 0 in component form. The requirement is that f of x equals fma, which equals 0, and F of y equals MAY, which also equals 0. So you sum up the forces in X, you sum up the forces in Y, that should equal 0. So going back to this problem, which is the correct free body diagram for the situation? I said that it's not E because F net equals 0 hat, but there's no forces shown. So this is not correct because there's no diagram there. There are forces in the problem, but they are balanced. So the answer is B, not E, because E makes it look like there are no forces. But in fact, there are several different forces acting on these, and they are balanced. So that is why E is not correct. Even though I don't think 0 can be a vector, I'm going to ignore that because that's a minor technicality. Whatever. So this is critical. Figure out what you know and what you don't know. A lot of problems have extra information that you really don't need. So determining what's important to solve the problem is the first step. Figure out what you know, what you don't know, and what you need to figure out. Okay. And if you have two things that you don't know, you're going to need at least two equations to solve for those. So if you have two unknowns, you need two equations. You can't do it with one equation. You might need X and Y components of force. So assess, check that your result has the correct units. Is it reasonable? And answer the question. So do you end up with the units of a Newton? What are the units of a Newton? Let's take a look at that. Okay, so let's look at our units here. We know that force has the units, and when I draw this sign, this is from applied math, and this we want to know what does F have, what units is. That is newtons. Force are always in newtons, but what is a Newton comprised of? A Newton can be written in terms of other units. So if we look at what force is made out of, we have mass. So the SI unit for mass is kilograms, right? And then acceleration is meters. So we'll do dot meters per second squared. Okay. So a Newton has the unit of kilograms times meters per second squared. If you don't end up with kilograms times meters per second squared, you probably did something wrong. If you have meters per second, not right. There is definitely an issue. So check your units. See if you have force. 1 Newton is kilograms per meter per second squared. Okay, let me erase this stuff. There we go. An orangutan weighing 500 newtons hangs from a vertical rope. What is the tension in the rope? What is the tension in the rope? The orangutan is at rest, so it is in static equilibrium. The net force on it must then be 0. We'll use this fact to find the tension. So that means, what can we say? What is the tension going down on the orangutan? Well, we know that the force going down has to be, if we approximate our orangutan by a dot, then it's going to be mg. All right, and that was supposed to be pointing down, but it's close enough. So that means that the tension going up has to be equal and opposite. So tension has to equal m times g. If we sum all of our forces, okay, then we're going to have tension minus mg. That's going to be 0. That's good. So the sum of our forces, if we tension minus the weight is equal to 0. That's what we want. All right, here we go. Prepare. The figure identifies the forces acting on the orangutan, the upward force of the tension in the rope, and the downward, a long-range force of gravity. the orangutan's weight, W, which is M times G, that's weight, we know that. All right, these forces are then shown in a free body diagram where it's noted that equilibrium requires F net equals 0, the 0 vector. Yes, we're going with 0 vector. Let's just accept it and move on. Even though 0 doesn't have units, whatever. So I guess it's a vector that points nowhere. It has no magnitude and points nowhere. Neither force has an x component, so we need to examine only the y components of the forces. In this case, the y component of Newton's second law, the sum of Fy is tension plus the weight equals 0. So the mass times acceleration is 0. It's not accelerating, it's in equilibrium. We did this. So we know that the tension in the weight has to be equal to 500 newtons. M times G, we know what the weight of the orangutan was in newtons, at least that's what I'm assuming. Yes, 500 newtons. So therefore, the tension in the rope is 500 newtons. Forces up equals equal, the forces up equal the forces down. We did it. Yes, we've done it. All right. It's not surprising that the tension in the rope equals the weight of the orangutan. No, it's not. All right. Conceptual example 5.3, forces in static equilibrium. A rod is free to slide on a frictionless sheet of ice. One end of the rod is lifted by a string. If the rod is at rest, which diagram in the figure below shows the correct angle? Oh, that is a tricky one. All right, so a rod is free to slide on a frictionless sheet of ice. Well, let's take a wild guess here. Okay, so we need to think about where the center of mass of this thing is. Where is it? Okay, because the center of mass is going to want to hang right below the rope. So we can imagine, okay, our tension's over here. The center of the mass is going to be over here. So we're definitely going to have, let's see, we'll put it here. And so it looks like we're going to have some tension going this way because here's our force vector. Okay, tension in the rope is going this way. So we're going to have an x and a y component, and it's not balanced. So our tension force, whatever this angle is here, theta, all right, that is going to be this way. There's nothing balancing it, okay? So I'd say it's definitely not this one, okay? So the tension in the rope for the y component, so we'll say the fx, this is the x direction over this way, is going to equal t times cosine of our angle theta, which is actually, I should have drawn, it doesn't matter. Could be that angle, we'll go with that one, but whatever. This is not balanced. There's clearly a force there and there's nothing pushing back on it, so it's gonna oscillate back and forth. What about this one? Well, the center of mass is right here, and the tension in our rod is straight up and down. There's nothing putting it over here, so indeed it could be this one. If this is holding it up over here, this is straight down, okay? There's no x component of the force, so we've got mg here, okay? And then we've got our tension force going up this way. It doesn't appear that there's any forces in the x direction. Now over here, let's say, we've got our tension going up at some angle theta here, okay? I don't know, it's looking like there's gonna be a force in the x direction. Yes, I think there will be. So we've got an angle here, theta. And so our force in the x direction, it looks like there is gonna be one. I'm seeing a force here, t equals cosine of theta. There's nothing balancing that out. So I think it will be that one. What does the survey say? Let's erase all of our work. Get rid of all of the drawings. There we go. We've done it. We can erase. And The survey says, oh, we missed it. Oh, there's no answer. Frictionless surface. I think it's A. We'll go with A because there's no, oh wait, here it is. Ah, there is an answer. Okay, let's start by identifying the forces that act on the rod. In addition to the weight of the force, the string exerts a tension on the force, and the ice exerts an upward normal force. What can we say about these forces? If the rod is to hang motionless, it has to be in static equilibrium. Yes, we've correctly identified it. In A, there's a net force to the left. In C, there's a net force to the right. And in B, there's no net force. So we've done it. I was thrown off there because I lost my face. Don't get lost. Remember, the tension always acts along the direction of the string, and the weight of the force always points straight down. The ice pushes up with a normal force perpendicular to the surface, but frictionless ice cannot exert any horizontal force. If the string is angled, we see that it is a horizontal component exerts a net force on the rod. Only in case B, where the tension and the string are vertical, can the net force be 0. The correct answer is B. We've done it. Yes. Oh, too far. Assess. If friction were present, the rod could in fact hang, as in case A and C, but without friction, the rod in these cases would slide until it came to rest in case B. For the case with no friction. All right. Example 5.4, finding the tension in a rope while towing a car. Yes. I believe in the textbook there is an incorrect table. Okay, now maybe it's correct. I'm not saying that it isn't not correct, but it might be incorrect. If you know what I'm saying. A car, so it's better if you just understand how to get these forces on your own, because if you look at the table in the book after this example, it was very confusing, and I think that they misprinted the table. Let's go ahead to the next slide and see if they got it right. Okay, they don't have the table in here. Oh, no, they do. Oh, yep, it's wrong in the book. Oh, yes, okay. So this table right here in the book is not correct. There's a misprint in the E textbook, which we're going to talk about right now. All right, so car with a mass of 500 kilograms is being towed at a steady speed by a rope held at 20-degree angle from the horizontal. A friction force of 320 newtons opposes the car's motion. What is the tension in the rope? Okay, so the car is moving in a straight line at a constant speed of A equals 0. So it is in dynamic equilibrium, and it must have a net force of MA equals 0. Okay. So this reminds me, of course, the time when I was much younger, and my stepdad was pulling me on his motor scooter, and I was on a skateboard. He was pulling me. I would do it now. Will I break my leg? That's always a question. Everything was fine. He was pulling me at a constant speed. We were in dynamic equilibrium until the manhole cover came. I had to go around it, and this caused me to fall off my skateboard at about 20 miles an hour. Of course, I was not wearing a helmet, but I didn't hit my head. I'm quite frankly lucky to be alive. Always wear your helmet when you're skateboarding or doing any other kind of adventure sport, because you do not want the force acting on your brain. Very bad. Always wear a helmet, my son. Okay, so we need to find this force that is counterbalanced by friction. So friction is opposing the tension in the car. So right away, we can say that if the car is in dynamic equilibrium, the force of friction going one way has to equal the force from the tension in the cable going the other way. This must be if it's in dynamic equilibrium. It's not accelerating. So they must be equal. All right, strategize. Car is moving in a straight line at constant speed. It's in dynamic equilibrium. Here are the facts. We know that F is the force of friction. Don't get confused. That would be bad. And that's really the key to this problem, is understanding that it is in dynamic equilibrium, because it says the car is being towed at a steady speed. That is what's important. Read the problem carefully. Sometimes I don't, and then you mess up. That's fine. The figure shows three constant forces acting on the car: the tension force, the friction force, and the normal force N, and the long-range force of gravity W. Those forces are shown in the free body diagram. Now, I will say in this problem that the normal force would not just be the weight of the car, because part of the tension in the cable is pulling it up. But it gives us a number for that frictional force. It says 320 newtons. So we don't care, because we have 320 newtons. That's the force of the car going in one direction. Okay, so let's draw our free body diagram. Oh, no, it didn't. Oh, no, fail. There we go. I've done it. I've clicked the button. So we know that we have a frictional force going this way. It's equal to 320 newtons. Okay? That has to equal the force due to tension going the other way. And look at this. We've got a triangle. Triangles are the best. Tension is running high. No, it's not. It's 20 degrees. That was funny. So we've got force going this way. What is the x component of our force? What did Pythagoras know? What other secrets did they have on that island in ancient Greece? I wonder. We'll never know, because only one cultist made it, and maybe he came to an untimely end. I don't know. I'm just saying it could have happened. If you want to talk about conspiracy theories, let's talk about math conspiracy theories. What did Pythagoras know on that island? If only more cultists would have escaped. All right, so we've got a triangle here. Yes, we do. So we can say that in the x direction, f of x opposing my frictional force there, it must equal t cosine of theta. This is the adjacent side, so therefore we know that it's got to be cosine. T is the hypotenuse of our triangle. We also have a force going this way from the tension, and that is going to be, so that'll be f of y is equal to t sine of theta. Yes, okay. So we wrote too much. I'm going to erase that. Too much on the slide. There we go. It's all gone. Okay. So we know what our x component of the force is. That has to equal our frictional force. Those two are equal and opposite because it's in dynamic equilibrium. So we add up all of our forces here. This is still an equilibrium problem, even though the car is moving. So our problem solving procedure is unchanged. All right. So let's look at the x component, the x component here, okay? So we have n of x plus t of x plus f of x plus wx. Wx is the weight of the car. N is, I guess, the normal force, even though there is no normal force in the x direction. Okay, so value of the x component, name of the x component, n of x, that's the normal force. It's 0 in the x direction. I don't know why they put it in there. That's really confusing, but whatever. I don't have as cool a shirt as that guy in the video, and my hair is definitely not that cool. That's fine. I'm okay with it. All right, what else do we have? the weight in the x direction, there's also no weight in the x direction. That's going to be a 0. And this is the correct table. So this is what should have been in the book. So now we have f of x, our tension here, T of x equals f of x, our frictional force. So F is our frictional force, and this is what we've got. T of x, we can see here, is T cosine of theta, as we talked about. Okay. Now let's look at our y components. In the y component, we do have our normal force in y. Value of the component is in. It's actually partly from the tension and whatever, but they just give us that in the problem, so we're not going to worry about it. We have tension in the y component. That's going to be T sine of theta. Okay. Then we have Fy and W. So our weight and the force of friction, I think that's F, the force of friction. It's 0 in the y direction. So what do we end up with? Okay, let's erase. Oh, erase. There is my face. Okay, let's get me back. All right, so here is our equation. With these components, Newton's second law becomes T cosine of theta minus F. This is our, this is in the x direction, and here, this is in our y direction, so we have xy. So we have the normal force plus T sine of theta equals our weight. So the weight is equal, so the normal force would, so the normal force, okay, let's rearrange this a little bit. It's going to equal the weight minus T sine of theta. And that's what I was talking about. That weight there is, so that means our normal force, what this means physically is our normal force is going to be less than it would be if the cable wasn't pulling up. Since the cable is pulling up, our normal force is going to be smaller because the cable is lifting it up off the ground. So therefore the ground is not pushing back on it as much. So because it's counteracting some of the weight. We have the weight pushing down, normal force pushing up, and it's decreased because our weight is gonna, the weight is still the same, but the normal force is gonna be smaller because there's less force pushing down on the ground because of the cable going up. So let's see, where's my, oh, there it is. We're in some weird mode. We want to draw, there we go. No, oh man, go back to the mouse. There we go. All right, we gotta erase this. I don't know what's going on. Oh jeez, okay. Oh, I gave it away. All right, so we're going to go back. Go back. Get back to where you came from. Get back. So we can solve for tension using the first equation. We know the force of friction. We know the angle. We get the tension. Two significant figures. Turned out that we did not need the y component of the equation in this problem. We would need it if we wanted to find the normal force in. Then we would need it. Oh, there we go. Where did I even go? Where are we? All right. Always good to know where you are. Assess, had we pulled the car with the horizontal rope, the tension would need to exactly balance the frictional force, 320 newtons, because we were pulling it at an angle. However, part of the tension in the rope pulls up on the car instead of in the forward direction. Thus, we need a little more tension in the rope when it's at an angle. So our results do seem reasonable. That's good. A ring seen from above is pulled on by 3 forces. The ring is not moving. How big is our force? Let's take a picture of the diagram. All right. We know that these have to be exactly balanced. Yes, they must. Forces up equal forces down. We've got 10 newtons going up. We've got some angle there. So let's fill in these triangles here. Oh, no. Oh, we messed it up. All right. Trying to draw. All right. So here's our force here. We've got a triangle here. Our force is going up, so it has to be sine. One force going up this way, the other one over here. We've got the same angle right there, so it's got to be 10 newtons times sine of theta times 2, because there's 2 cables, so it's going to be 20 newtons times sine of theta. Yes, we have done it. These 2 forces have to equal the force going down. All right, let's erase this. All right, a 100 kilogram block with a weight of 980 newtons hangs on a rope. Find the tension in the rope if the block is stationary. Then, if it's moving upward at a steady speed of 500 meters per second. All right, they're trying to trick you. This is a trick because it says if it's moving upward at a steady speed, 500 meters per second. You see, this is a common problem with movies in space, because they make it look like that as soon as you stop applying that rocket, so as soon as you stop applying thrust, you're out in space, there's no gravity, there's no forces acting. So as soon as they turn off the engine, all of a sudden the spaceship stops moving. This is wrong, okay? If you had on those thrusters, like in Star Wars, it's accelerating. If you turn them off, you'll just keep going at the same velocity, okay? So if you were headed at almost light speed, you're gonna keep on going right at light speed. They would have to turn the Star Destroyer around, blast the other way to slow down. Yes, you've got to turn the Star Destroyer around in order to slow down. So those giant triangular ships, they're accelerating, they're going light speed. Okay, if they want to slow down, they need to turn those thrusters around. They've got to slow it down. Okay, otherwise you're just gonna keep going. You can't stop otherwise. So that might be a problem. Maybe you would want your spaceship to be more round. So we've answered an important question here today. Why doesn't the Star Destroyer work as a triangle? It would seem that it's too long and bulky to turn around. Maybe they have thrusters on the side. I don't know. But if they want to stop, they've got to turn the Star Destroyers around, turn those thrusters on the other way, and slow it down. All right, but we were actually talking about blocks, not Star Destroyers, which is fine. So a 100 kilogram block with a weight of 980 newtons hangs on a rope. Find the tension in the rope if the block is stationary. Then if it's moving upwards at a steady speed. Why did they tell us that it weighs 100 kilograms and then they tell us the force it hangs on a rope? Okay, it has a weight of 998 newtons. Well, the answer is this. It's the same in both of them. The tension in the rope has to equal the tension going down. It doesn't matter if you're moving at a constant velocity. The tension is always balanced since it's at a constant velocity or it's stationary. Okay, and so it doesn't really matter which direction your thrusters are pointing. All right, dynamics of Newton's second law. The essence of Newtonian mechanics can be expressed in 2 steps. The forces acting on an object determine its acceleration. So A equals F over m. The object motion can be found using A in the equation for kinematics. Okay, so thus Newton's second law says F equals ma is the sum of F, all the forces, equals m ax, and the sum of all y forces equals m times ay, which is also equal to 0. So Newton's second law in component form. So the force is acting on an object determine its acceleration. Okay, A equals F over m. All right, problem solving approach 5.2, a dynamics problem. Dynamics problem use Newton's second law as a connection between forces and kinematics. Strategize. There are two kinds of dynamic problems. If the forces in an object are known, you can use Newton's second law to find the acceleration, and then from kinematic, the object's position and velocity. In the other case, you can calculate the object's acceleration from kinematics. Using the acceleration, you can apply Newton's second law to find the forces acting on the object. All right, sounds simple enough. In both kinds of problems, the approach to the solution is the same. So find the force. Use the kinematic equations if you must, but you may be given the forces in the beginning. All right. Always remember. All right. Sketch a visual overview consisting of a list of values that identifies known quantities and what the problem is trying to find. So what don't you know? What are you solving for in the equation? Because that's a place where you can get lost. Write down what you do know. Sometimes the problem will give you information that's redundant or you don't need to know it. That last problem with the block hanging down, it said it had a weight of 98 newtons or 980 newtons. Well, that would mean that its mass must be 100 kilograms. So why did it tell us that its mass was 100 kilograms? It didn't weigh 100 kilograms. Its mass was 100. Okay, so draw your force components. Draw your force diagram, and then write down everything you know. A force identification diagram to help you identify all forces acting on the object, and a free body diagram that shows all the forces acting on the object. So this is really important. You're probably going to need to use the kinematic equations to find velocities, positions, and you'll also need to make a sketch. Okay, so always draw a picture and think about which one of those 5 equations that you can use to solve the problem. You don't always need to solve for the final velocity. Sometimes you can get away with not worrying about velocity. Other times it makes it easier. So think about how you can do the problem in the least amount of steps. That's a good philosophy for physics. Be as lazy as possible. Don't do extra steps if you don't have to. And part of that comes with experience, knowing when to use what equation, but sometimes it's easier just to use an equation that doesn't have the velocity that just goes away. Okay, so what am I talking about exactly? So to show you what I mean, I'm looking at the Khan Academy website. That's khanacademy.org. And they give some really great examples of how to use the 5 kinematic equations. So if we look at these expressions, the first one is V equals V0 plus AT. This formula is missing an X. So that means that if you're not given distances in your problem, this might be an equation that you would want to use. Let's go ahead and write that equation out. So V equals V0 plus AT. I've seen a lot of people using this to get to find the time when you get to a certain velocity. And in some situations, that's a good idea. But another equation that you could use was equation number 3. So this was equation number 1. This is equation number 3. Delta x equals V0t plus 1/2 AT squared. This is a good expression to use if you know that your particle, or whatever it is, starts at rest, because that means that this term will go away. So this should be a t right there. That means if it's at rest, v0 equals 0 if the object is at rest. So sometimes it's better to use this equation. For example, if you know the distance, right? And this works in x and y. So if you have acceleration, you can use this. You can also use it for projectiles. So this is often a very handy expression. So if you don't have any acceleration, so in the x direction, right? So here's 2. Then we've got delta x is going to equal v plus v0 over 2 all times t. This is good in the x direction if you only have a velocity and there's no acceleration, okay? Then the final one, if you're missing a time or you just don't want to find the time, then you can use this expression, v squared equals v0 squared plus 2a delta x. So it seems like everybody sort of has their favorite equation that they like to use. Mine is probably this one. This is my go-to equation. I always try and solve this one first. This one is probably my least favorite, if I had to rank the kinematic equations. Well, that's going to bring us to the end of our broadcast tonight. But thank you for watching. This concludes episode 13. Tune in tomorrow for episode 14, where we will finish talking about chapter 5, Newton's laws applied to equilibrium, cases of dynamic equilibrium and static equilibrium. Thanks for watching. See you tomorrow.
Thank you. Like and subscribe down below.